Hello viewers, in this video lecture today we are going to talk about the massive open online courses on emerging technologies in renewable energy sources. Name of the subject domain is biomass energy, and today we are going to discuss the topic that is biomass conversation. So viewers, here are the important topics which will be discussed in this video. First, introduction, then biomass conversion, combustion of biomass, methods of biomass conversion, direct combustion of biomass, thermochemical processes, biochemical processes, chemical conversion, electrochemical conversion. So start from the introduction. Biomass can be regarded as many organic material that originated from plants or animals. The United Nations Framework Convention on Climate Change in 2005, they defined it as follows: a non-fossilized and biodegradable organic material originating from plants, animals and microorganisms. This shall also include products, byproducts, residue and waste from agriculture, forestry and related industries, as well as the non-fossilized and biodegradable organic fractions of industrial and municipal waste. The world's energy demand has been steadily increasing in the last several decades. This is due to rapid increase in industrialization, population and the quest for improvement of the living standard for societies. On the other hand, this has caused an irreversible damage to the environment which leads to global warming and climate change. These issues have been the topic of discussion among scientists and policy makers at national and international levels on how to mitigate the problem. The modern society is emphasizing on shift from non-renewable to renewable energy such as wind, solar, tide, geothermal and biomass in their search for energy sources. Before the discovery of fossil fuels such as petroleum products, coal and natural gas, biomass was the main source of energy for heating and cooking. Biomass is the term used to describe all materials that contains carbon in an organic form. This organic form of carbon can be transformed into inorganic through photosynthesis by forming bonds with other elements such as hydrogen and oxygen using solar energy. The demolishing of these bonds through physical or biological means cause a closure in the cycle and making CO2 to be regenerated. During the regeneration process, energy is released which can be converted into other forms of energy. Therefore, as long as this equilibrium is maintained between use and regeneration, biomass is a renewable or inexhaustible source of energy. It is expected to be the leading form of energy with a significant global energy load of about 10 to 15%. However, biomass has a share of about 90% of the total energy requirement for remote and rural areas of the developing countries. Therefore, it is likely to remain the future leading source of energy feedstock for the developing countries, since about 90% of the world population is expected to live in the developing world by 2050. Biomass accumulates chemical energy in form of carbohydrates through combination of solar power and carbon dioxide during the process of photosynthesis. This has made it to be a potential energy source, since the carbon dioxide captured during photosynthesis could be released when it burns. It is cheap and available in all forms such as forest and agricultural residue, wood, byproduct of biological material, organic components of municipal and sludge wastes. There are several ways to convert biomass into useful product, which largely depends on biomass characteristics and the end product. The technologies applied in the conversion of biomass are mainly categorized under thermochemical or biological methods. Let us understand what is biomass conversion. Biomass conversion to biogas is a natural process that utilizes a consortium of anaerobic bacteria working in equilibrium to degrade complex biomass into simpler compounds, which are then converted to biogas and a liquid residue rich in very useful metabolism. But in recent years, the option of co-producing biohydrates in the whole anaerobic process has been explored for commercial viability because of the significantly higher value of hydrogen. Even if produced in relatively small volumes, not yet profitable to be marketed on its own. Biohydrogen can be added to biomethane to produce biohythane, which has higher combustive properties than methane alone. Applying the anaerobic process for the purposeful conversion of biomass to biogas requires process engineering approaches in designing and operating favorable system conditions for high yield and productivity. The anaerobic process applications and the advancements made to add value to the products, maximizing the biogas options with biomethane, biohydrogen and biohythane, and also results in a better digested sludge residue, which can be further exploited for income generation and to make the entire process system with zero emissions. The next, we can move method of biomass conversion. So, biomass combustion of biomass used to heat greenhouse. Combustion of biomass is arguably the oldest known and most widely used controllable energy source on earth. In recent years, rising cost of fossil fuels and the development of advanced equipment have made biomass combustion an economical, efficient and practical energy source. Principle of combustion, we know that combustion is familiar to all of us, but many do not realize that it is essentially a chemical reaction. In the process of combustion, two ingredients, biomass and oxygen, are combined in high temperature environment to form carbon dioxide, water vapor and heat. The amount of heat that is produced varies depending on species, climate and other factors, but it is generally about 20 megajoule of energy per dry kilogram of biomass. In order for combustion to be efficient and clean, the ingredients must be well mixed at the right temperature for the right amount of time. Practically, this means that you need the right amount of fuel, the right amount of air and the right conditions. Water content in biomass is an important factor when it comes to combustion. The best burning fuels are dry. However, biomass almost always includes some amount of moisture. For example, green wood chips are usually about 50% water and 50% dry matter. Fresh leaves from a plant can be as high as 95% moisture and 5% dry matter. Ideally, biomass should be no more than 20% moisture. Feedstock from biomass combustion, in this a feedstock is merely the fuel that will be burned from energy. While wood is the most common feedstock for biomass combustion, almost any plant material can be used as a combustion feedstock. Processing biomass for combustion, in this biomass can often benefits from a certain amount of processing to make it more suitable as a combustion fuel. This includes sizing, drying and or densification. There are currently three types of biomass conversion technologies available that can result in specific energy and potentially renewable products. Moving on the next, direct combustion process. Direct combustion furnaces can be divided into two broad categories and are used to produce direct heat or steam. In this, Dutch ovens, spreaders, strokes and fuel cell furnaces use two stages. The first stage is for drawing and possible partial gasification, and the second is for complete combustion. More advanced version of this system use vibrant rotator grates to facilitate ash removal, some of which require water coolings. The second group includes suspension and fluidized bed furnaces commonly used with fine particle, biomass feedstock and liquids. In suspension furnaces, the particles are burned while being kept in suspension by injection of turbulent preheated air into which the biomass particles may already be mixed. In fluidized bed combustor, a boiling bed of preheated sand at a temperature of 500 to 900 degrees Celsius provides the combustion mediums into which the biomass fuels are either dropped if it is dense enough to sink into the boiling stands, or particles or liquids if injected. Moving on the next topic, that is co-firing. Modern practices that have allowed biomass feedstock an early and cheap entry point into the energy market is the practice of co-firing a fossil fuel, usually coal, with a biomass feedstock. There are many advantages to co-firing, especially where the power output is the first, where the conversion facility is located near an agro-industrial or forestry product processing plant. There is a large amount of low-cost biomass residual available. These residual may represent a low-cost fuel feedstock, although there may be other opportunity cost. Second, it is now widely accepted for that fossil fuel power plants are generally highly polluting in terms of sulfur, CO2 and other GHF. The use of existing equipment, perhaps with some modifications, and co-firing with biomass could represent a cost-effective means to meet more stringent emission targets. The low sulfur and nitrogen relative to coal content of biomass fuels and near zero net CO2 emission levels allow biomass to offset the high sulfur and carbon content of fossil fuel. The third, if an agro-industrial or forestry processing plant wants to make more efficient use of residues generated by cogeneration electricity, but has a highly seasonal component to its operational schedule, co-firing with fossil fuel would allow economic production electricity throughout the year. Agro-industrial processes such as the cane sugar industry can produce large amount of electricity during the harvesting and processing season, and however during the off season the plants will remain idle. This has two drawbacks. The first, it is an inefficient use of equipment that has a limited lifespan, and the second, power distribution utilities will not pay the full premium for power supplies that cannot be relied upon for year-round production. In other words, the distribution utility needs a guarantee of supply throughout the year and therefore may have to invest in its production capacity to cover off-season gaps in supply, along with associated cost in equipment and fuel. If agro processors can guarantee a year-round power supply through the burning of alternative fuels, it will make efficient use of its equipment and receive premium payments for its electricity by the distribution facility. Moving on the next, conversion technologies. There are a number of technological options available to make use of a wide variety of biomass types as a renewable energy sources. Conversion technology may release the energy directly in the form of heat or electricity, or may convert into another forms such as liquid biofuel or combustible biogas. While for some classes of biomass resource there may be a number of usage options, for other there may only one appropriate technology. Next is thermochemical conversion, or we can say thermal conversion. So thermochemical processing is the use of heat to promote chemical transformation of biomass into energy and chemical products. Thermal biomass conversion processes use heat as the key mechanism to upgrade biomass into better and more practical fuels. These are processes in which heat is the dominant mechanism to convert the biomass into another chemical forms. The basic alternatives are separated principally by the extent to which the chemical reactions involved are allowed to proceed, like pyrolysis, gasification, combustion and liquefaction. So energy created by burning biomass is particularly suited for countries where the fuel wood grows more rapidly. Example, tropical countries. Biomass co-firing with coal by contrast typically occurs at efficiencies near those of the coal combustor. There are a number of other less common, more experimental thermal process that may offer benefits such as hydrothermal upgrading and hydroprocessing. Some have been developed for use on high moisture content biomass, including aqueous slurries, and allow them to be converted into more convenient forms. Moving on the application of this thermal conversion, the first combined heat and power, that is also called CHP, and co-firing. Now we can understand this, what is pyrolysis. So the process of heating biomass in the absence of air is known as pyrolysis. During this process, the biomass is transferred into solid, liquid and gaseous fractions. Using flash pyrolysis, which could convert the biomass into biocrude with a maximum efficiency of 80%, bio-oil can be produced using pyrolysis. Bio-oil may be used in turbines and engines as well as the feedstock for industries. The biomass feedstock are subjected to high temperature at low oxygen level, thus preventing complete combustion, and can be done under pressure. Biomass is degraded into single carbon molecules and hydrogen is producing a gaseous mixture called producer gas. Carbon dioxide can also be produced, but it is reduced back to CO and H2O under the pyrolytic condition of the reactor. This water further aids in the reaction. Liquid phase products arise from temperatures that are too low to break down all long chain carbon molecules, it resulting in the production of tar, oil, methanol and acetone. Once all the volatile is removed, the residual biomass takes the form of char, which is virtually pure carbon. Pyrolysis has recently attracted attention for the production of liquid fuels from cellulose feedstock by fast and flashes, pyrolysis in which the biomass has a short residue time in the reactor. A more detailed understanding of the physical and chemical properties that govern pyrolytic reactions has allowed optimization of the reactor conditions required for this type of pyrolysis. Further, work is now focusing on the use of high pressure reaction condition to produce hydrogen and low pressure catalytic techniques requiring zeolites for alcohol production from pyrolytic oil. The next is our gasification. Biomass gasification involves burning of biomass in a limited supply of air to give a combustible gas consisting of carbon monoxide, carbon dioxide, hydrogen, methane, water, nitrogen along with contaminants like small char, particles, ash and tars. The gas is cleaned to make it suitable for use in boilers, engines and turbines to produce heat and power. Biomass gasification provides a means of deriving more diverse forms of energy from the thermochemical conversion of biomass than conventional combustion. The basic gasification process involved devolatilization, combustion and reduction. The production of gasification are a mixture of carbon monoxide, carbon dioxide, methane, hydrogen and various hydrocarbons which can then be used directly in gas turbines and boilers, and also it used as a precursors for synthesizing a wide range of other chemicals. Incomplete oxidation of biomass at extreme temps to create a variety of flammable gases is known as gasification. Low calories gas can be used as fuel for power plants. Syngas can be composed of biomass. Syngas made from biomass is used to create methanol and hydrogen, two fuels that can be utilized for transportation and other purposes. Due to the high temperature and control environment, almost all the raw material is being converted into gas. This happens into two stages. In the first stage, the biomass is practically combusted to produce productive gas and charcoal. In the second stage, the CO2 and H2O produced in the first stage are chemically reduced by charcoal forming CO and H2. The composition of the gas are 18 to 20% hydrogen and equal part of CO, 2 to 3% of CH4, 8 to 10% of CO2 and the remainder is nitrogen. These phases are specially separated in the gasifier, with the gasifier design relying heavily on the feedstock characteristics. The gasification requires a temperature of around 800 degrees Celsius and is carried out in a closed top or open top gasifier. This gasifier can be operated at atmospheric pressure or higher. The gas energy density is typically less than 5.6 megajoule per meter cube, lower than natural gas at 38 megajoule per meter cube, which provides only 60% of the diesel power rating when used in modified diesel engines. Gasification technology has existed since the turn of the century, when coal was extensively gasified in Britain and elsewhere in homes for electricity generation and cooking and lighting. The gasifier was used extensively for transport in Europe during World War II due to oil shortage, with a closed top design being the predominant one. Gasification of biomass takes place in a restricted supply of oxygen and occurs through initial devolatilisation of the biomass, combustion of the volatile material and char, and further reduction to produce a fuel gas rich in carbon monoxide and hydrogen. This combustible gas has a lower calorific value than natural gas, but can still be used as fuel for boilers, for engines, and potentially for combustion turbines after cleaning the gas stream of tars and particulates. There are two main types of gasifier that can be used to carry out this conversion: fixed bed gasifier and fluidized bed gasifier. The conversion of biomass into a combustion gas involves a two-stage process. The first, which is called pyrolysis, takes place below 600 degrees Celsius when volatile components contaminated within the biomass are released. These may include organic compounds, hydrogen, carbon monoxide, tars, and water vapor. The combustion biomass is an oxygen-rich atmosphere is known as combustion. It is used in a number of processes and equipment, including furnace, burner, steam boilers, furnaces, turbines, to convert chemical energy that is stored in biomass into heat energy, mechanical energy, and electric power generation. Despite any kind of biomass could be burned, it is only feasible to burn biomass when the humidity is under 50%. Then biochemical conversion methodologies are more suited to high moisture content biomass. Combustion and gasification operating together to produce a net efficient of 40 to 50% ensure a high conversion rate. Conventional combustion technologies raise steam through the combustion of biomass. This steam may then be expanded through a conventional turbo alternator to produce electricity. A number of combustion technology variants have been developed. Underfeed stokers are suitable for small boilers up to 6 megawatt. Great type of boilers are widely deployed. They are relatively low investment cost, low operating cost, and good operation and partial loads. However, they can have higher NOx emissions and decreased efficiencies due to the requirement of excess air, and they have lower efficiencies. Fluidized bed combustor, which use a bed of hot inert material such as sand, are a more recent deployment. Bubbling FBCs are generally used at 10 to 30 megawatt capacity, while circulating FBC are more applicable at larger scale. Advantage of FBC are that they can tolerate a wider range of poor quality fuel while emitting lower NOx levels. During combustion, the volatile and char are partially burned in air or oxygen to generate heat and carbon dioxide. In the reduction phase, carbon dioxide absorbs heat and reacts with the remaining char to produce carbon monoxide. The presence of water vapor in gasifier results in the production of hydrogen as a secondary fuel component. Then the next method is liquefaction, or we can say liquefaction. Hydrothermal liquefaction of biomass is the thermochemical conversion of biomass into liquid fuels by processing in a hot pressurized water environment for sufficient time to break down the solid biopolymeric structure to mainly liquid components. Typical hydrothermal processing conditions are 520 to 647 Kelvin of temperature and operating pressure from 4 to 22 megapascal of pressure. Closely related processing in supercritical water conditions will not be discussed in this review except the context of aqueous phase processing. The process is meant to provide a means for treating wet material without drying and to access ionic reaction conditions by maintaining a liquid water processing medium. The temperature is sufficient to initiate pyrolytic mechanism in biopolymers, while the pressure is sufficient to maintain a liquid water processing phase. Hydrothermal processing is divided into three separate processes depending on the severity of the operating condition. At temperature below 520 Kelvin, it is known as hydrothermal carbonization. The main product is a hydrochar which has a similar property of that of a low rank coal. In the case of microalgae, the hydrochar is largely produced from the carbohydrate and proteins fraction. The lipid fraction is still intact, making it possible to extend the lipids prior to hydrothermal carbonization. At intermediate temperature ranges between 520 and 647 Kelvin, the process is defined as hydrothermal liquefaction, resulting in the production of liquid fuel known as biocrude. Biocrude is similar to petroleum crude and can be upgraded to the whole distillate range petroleum derived from products. At higher temperature above 647 Kelvin, gasification reactions start to dominate and the process is defined as hydrothermal gasification, resulting in the production of a synthetic fuel gas. It is a process that generates a liquid from solid or a gas that generates a non-liquid phase which behaves in accordance with fluid dynamics. This technology has the potential to produce high quality products of greater energy density. This product should also require less processing to produce marketable products. Then catalytic liquefaction are a low temperature, high pressure thermochemical biomass conversion process performed in the liquid phase. This requires either a catalytic or a high hydrogen partial pressure. Technical problems have limited the opportunities for the technology so far. Moving on the next slide, biochemical conversion. As biomass is a natural material, many highly efficient biochemical processes have developed in nature to break down the molecules of which biomass is composed, and many of these biochemical conversion processes can be harnessed. Biochemical conversion of biomass involves use of bacteria, microorganisms and enzymes to break down biomass into gaseous or liquid fuels such as biogas or bioethanol. The most popular biochemical technologies are anaerobic digestion and fermentation. Anaerobic digestion is a series of chemical reactions during which organic material is decomposed through the metabolic pathways of naturally occurring microorganisms in an oxygen depleted environment. Biomass waste can also yield liquid fuels such as cellulose ethanol, which can be used to replace petroleum based fuel. Biochemical conversion makes use of the enzymes of bacteria and other microorganisms to break down biomass. In most cases, microorganisms are used to perform the conversion process. Biochemical process take place when there are chance encounters between enzymes and substrates. The use of microbes to produce ethanol is an ancient art. However, in recent times, such as organisms have been regarded as biochemical factories for the treatment and conversion of most forms of human generated organic wastes. The use of microbes to produce ethanol is an ancient art. However, in the recent times, such as organisms have been regarded as biochemical factories for the treatment and conversion of most forms of human generated organic wastes. Microbial engineer has encountered the use of fermentation techniques, aerobic and anaerobic, for use in the production of energy and fertilizer and in the removal of unwanted products from water and waste stream, like anaerobic digestion and ethanol fermentation. So, in the anaerobic digestion, hydrocarbon is immediately converted to a biogas during anaerobic digestion. It consists primarily of methane and CO2 with teeny quantities of other gases including H2S. Bacteria metabolize biomass in anaerobic environment, forming a gas with equal energy 20 to 40% of the material's lower heating value. Anaerobic digestion is the extensively utilized commercially tested technology that produces grid connected electricity with a least capacity of 1 megawatt. Then anaerobic reactors are commonly used to produce methane containing biogas from manure and crops residue. They use mixed methogenic bacterial cultures that are characterized by defined optimum temperature ranges for growth. These mixed cultures allow digester to operate over a wide temperature range, that is from 0 degree to 60 degrees Celsius. When working well, the bacteria convert about 90% of the feedstock energy content into biogas, an easily usable energy source for cooking and lighting. The sludge produced after the manure passed through the digester is non-toxic and odorless. In addition, it loses relative little nitrogen or other nutrients during the digestion process, making it a good fertilizer. In fact, digester sludge has a higher nitrogen content than animal manure and it left to dry in the field. Many nitrogen compounds in fresh manure evaporated during drying in the sun. On the other hand, some of the nitrogen in the digested sludge is vaporized and some of the nitrogens are converted into urea. Now moving on the chemical conversion. A range of chemical processes may be used to convert biomass into other forms, such as to produce a fuel that is more conveniently used, transported or stored, or to exploit some property of the process itself. In most cases, the first step involves gasification, which step generally is the most expensive and involves the greatest technical risk. Biomass is the more difficult to feed into a pressure vessel than coal or any liquid. Therefore, biomass gasification is frequently done at atmospheric pressure and cause combustion of biomass to produce a combustible gas, and it consisting of carbon monoxide, hydrogen and traces of methane. This gas mixture, called a producer gas, can provide fuel for various vital processes such as internal combustion engines as well as the substitute for furnaces, oil in direct heat applications. Because any biomass material can undergo gasifications, this process is far more attractive than ethanol or biomass production, where only particular biomass material can be used to produce a fuel. In addition, biomass gasification is a desirable process due to the ease at which it can convert solid waste, such as wastes available on a farm, into producer gas, which is a very usable fuel. And the last, electrochemical conversion. In addition to combustion, biomass or biofuels can be directly converted to electrical energy via electrochemical oxidation of the material. This can be performed directly in a direct carbon fuel cell, direct ethanol fuel cell or a microbial fuel cell. The fuel can also be consumed indirectly via a fuel cell system containing a reformer which converts the biomass into a mixture of carbon monoxide and hydrogen before it is consumed in the fuel cell. Thanks for watching this video.